Funny the way that I feel now. Can't keep my feet on the ground. Everything seems unreal now when you're not around. Daydream, why do you haunt me so? Deep in a rosy glow, the face of my love you show. Daydream, I walk along on air, building a castle there for me and my love to share. Don't know the time, Lordy, I'm in a daze. Sun in the sky, while I moon around feeling hazy. Daydream, don't break my reverie until I find that she is daydreaming just like me. Don't break my reverie until I find that she is daydreaming just like me.
So if we could please take a seat. Jasper. Hello and welcome to the 4th annual Michio Yanai Distinguished Lecture. I'm Jochen Stutz. I'm the chair of the Department of Atmospheric and Oceanic Sciences. And I'd like to first thank you all for coming here and joining us for this exciting talk. So tonight's lecture honors the memory of Michio Yanai, who was an expert in tropical meteorology and a professor in the department from 1970 to 2010. And I'm especially honored to welcome Michio's wife Yoko and their son Satoshi, who are joining us here today. And I would especially like to thank you for making this event possible. It's something that the department really enjoys, and especially having somebody as distinguished as Mike here and being able to chat with him while he visits the department. Really, all our students and professors really enjoy that. So thank you very much. And as many of you know, Michio left a legacy of really groundbreaking work in tropical meteorology that is very highly relevant today. And he was also a very esteemed colleague in the department and collaborating with a lot of the professors here, and also left a mark in education, educating some of the next generation of atmospheric scientists. And two of these people, Robert Fowell, who was a colleague of ours in the department, is now at SUNY Albany, and Michio's former students, Wenwen Tang, worked for several years to put together a monograph of the American Meteorological Society honoring Michio's research. And the title of the monograph is Multiscale Convection Coupled Systems in the Tropics. And I am not sure if you guys actually have seen it, but we just got the first copy 2 days ago, thanks to Jeff, who made it sure. So I would like to give you the first monograph that we received, and it actually turned out to be very beautiful. And thank you. And at this point, I'd like to introduce you to Professor Conan Liao, who is a distinguished professor in our department and also the director of the, and I always have to look this up because we always call it CHIFRES, the Joint Institute for Regional Earth System Sciences and Engineering, and he's going to introduce today's speaker. Conan, please.
My name is Conan Liao, and in my capacity as chair of the selection committee, it is my great pleasure and distinct honor to welcome and introduce 2017 Michio Yanai lecturer, Professor Mike Wallace from the University of Washington. Mike was a weather nut, just like Michio Yanai, and received his PhD in meteorology from MIT in 1966, and then went to the University of Washington as assistant professor and stayed there for more than 50 years. In terms of his academic leadership, Mike was chair of the Atmospheric Sciences Department for 5 years and concurrently served as director of the Joint Institute for the Study of the Atmosphere and Ocean from 1982 to 1997, and later from 2003 to 2006. From 1997 to 2000, Mike was co-director for a program on the environment. You can see his breadth of his academic this involvement. Mike discovered a number of paradigm shift atmospheric processes based on data analysis. And let me name three. Pacific North American pattern, Wallace and Kastler, 1981. Pacific Decadal Oscillation, Horror and Wallace, 1981. Zhang, Wallace et al., 1997. And Arctic Oscillation, Thompson and Wallace, 1998. Of course, his textbook and introduction, Atmospheric Sciences, and introductory survey, first and second edition, Wallace and Happ, 1997 and 2006, is well known in atmospheric sciences and has been widely used for graduate level introductory courses. For all his original contributions, Mike was recognized by the AGU James McEwen Medal in 1972, the AMS Meisinger Award in 1975, NSF Creativity Award in 1987, and AMS Raspy Medal in 1993, and the Roger Ravio Medal in 1999. He was elected a fellow of the American Academy of Arts and Sciences in 1997 and a member of the National Academy of Sciences in 1998. For his academic and research contribution, the John M. Wallace Hall at the University of Washington is named after Mike. As a scientist, Mike is also concerned about the societal impacts and adds a human dimension to the pursuit of academic and research excellence. In the 2017 Michio Yanai Distinguished Lecture, he will be presenting El Nino Comes of Age. Professor Mike Wallace.
Thank you. Well, I should say that it is a real honor for me to be here as the Michio Yanai lecturer this year. And I think the thing that gives me the greatest pleasure is that it brings me back to a long friendship that we enjoyed going back to the late 1960s. And so I thought I would start by just giving a little background of how we met. And so I'd like to start with a photo. This was circa 1969, and the this is, I guess was as even thinner then than I am now, so you can recognize me. So this is Richard. Here we go. This standing in the middle is Richard Reed. He was our senior sort of tropical dynamicist at the University of Washington at that time. Very distinguished career in his own right. And I think he's the reason all the rest of us were there, because he's talked the department into having a couple of extra faculty positions in this area. Jim Holton got the first of these, and I got the second. And this is my first graduate student, Vernon Kowski, who had just started a year before that. And this is C.P. Chung, who was the chairman for many years at the Naval Postgraduate School in Monterey. And so we were working on tropical waves at that time. And Holton and I were finishing a paper that was a totally unsuccessful paper where we ended up disproving the paradigm that we tried to prove. And we realized, and it was really Jim who realized, that we needed to explain this mysterious quasi-biennial oscillation in the stratosphere over the equator. We needed something really exotic. We needed a new kind of wave that would supply the momentum to bring it downward. And just coincidentally, within a few months of when this photo was taken, we saw it was Jim Holton who noticed an article in the Journal of the Meteorological Society of Japan by this new person for me, Michio Yanai, and his graduate student Takito Maruyama, in which they presented some time height sections of wind at a station over the equator, Kapinga-Marangi, at 1 degree north. And this is the lower stratosphere, starting about the base of the stratosphere and going up into the middle stratosphere. And these are wind vectors as we used to plot them then. In fact, probably hand plotted. And the very faint dashed areas are where the wind is blowing has a component from the south. And the undashed areas, the clear areas, are where it has a component from the north. And so you can see these bands of grayness coming down, which is an indication of waves where the wind undulates back and forth between north and south. And the waves propagate downward over a period of a few days. These are calendar dates here. And with a period of about 4 or 5 days. Well, if this had been just a purely observational paper, it would have been still a famous paper. But Michio went a step further, and he identified these waves with one of the waves in a family of waves that were identified by his colleague who graduated from University of Tokyo a year before him, Taro Matsuno. And Matsuno had published a paper just a couple of years before with these solutions to the family of waves that would exist on the equator on a rotating planet. And this was the gravest member of that family of waves, maybe think of it as the oldest child, perhaps. And this was the next. And the family goes on. There are a couple of dozen of them that would be worth describing if I were doing a course. But I'll just show these two. And Michio recognized that these waves were the embodiment of this number 2 member of the family. And here along the equator, you see the shifting winds, northerly, southerly, northerly, southerly. And he pictured these, and these waves propagate along the equator from actually these go from east to west. And so he said that these waves are what Matsuno referred to as the mixed Rossby gravity wave. And then about a couple of months later, Vernon Kowski, in the previous picture, my graduate student, based on hand analyses, had made a diagram somewhat like this one that turned out to be the other member of the family, what Matsuno called the Kelvin wave. And it was actually Jim Holton who recognized that because Kowski had shown him nice diagrams like this for the U component of the wind, the zonal component, and for temperature. And Holton said, well, where's the one for V, the counterpart of this? And Kowski said there isn't any. The wind, the meridional wind doesn't do anything. So he immediately recognized that this was the wave. So based on the discovery of those two waves, Holton with the young rising dynamic superstar Richard Lindzen, they wrote within a couple of years after that a paper explaining the quasi-biennial oscillation on the basis of those waves. Well, a jump from that to 2010, and this photograph was taken at the University of Washington, and of course here is Michio, and here is Matsuno, the theoretician who identified those waves. And here's me, and here's C.P. Chang, who took the photo, who was in the previous photo, and who actually supplied that photo to me. He is the one who had saved it. And this is Gabriel Lau, another one of my students. I was so touched that Michio came and took part and actually gave a talk in birthday symposium for me when I turned 70, and that was the occasion for this picture, October 1970. So that is in way of an introduction. I should say that Michio was a good friend over the years. He was the sole reviewer on a review paper that I wrote for reviews of geophysics about these waves. And I must say he was a tough taskmaster as a reviewer. Everything in that article had to be just so. And I learned a great deal and gained in self-discipline by working with him and going through the many iterations. And our friendship survived all these iterations, and we had many good times afterwards. So my topic of my talk, El Nino Comes of Age. I just thought of this comes of age idea because this is something of an anniversary for a couple of significant events in the development of our knowledge of what we call, El Nino, and I'm later going to call ENSO in this lecture. And so the first step in that discovery goes back about 100 years, maybe not quite 100 years in terms of the published papers, but it might actually be close to 100 years in terms of the actual work that went into it. And the outstanding person of that era was Gilbert Walker, a British applied mathematician, a brilliant man who had done very important theoretical work on topics ranging from the flights of birds and boomerangs to climate. For those of you who have seen the movie The Man Who Knew Infinity by, I'm having a senior moment, the Indian mathematician Ramanujan. Walker was one of the people who interviewed him about the possibility of coming to England. Well, he, in his work in India, he did a lot of work with correlations, just simple correlation coefficients between time series of atmospheric variables at different stations. And he had a number of groups of correlations that he thought were particularly interesting. And this was, I think, his favorite, and he felt it was relevant to monsoon rainfall over India. And in any case, it was interesting enough to be worthy of study in its own right. So these are the names of the time series that were in his study. And the A centers are the strong ones, the ones he thought were really the most solid. And then he had a second tier of them. And the ones that have the same algebraic sign here, these are the correlation coefficients. The ones with the same sign go up and down together. And the ones with opposite correlations, like the first two, they're like a seesaw. One goes up, the other goes down, and so on. Well, so this subset of these, which are the strongest of them, and the ones he put right at the top of the list, the three of these are really pressure at the west end of the Pacific. Stations Batavia, that was the modern-day Jakarta, Manila, Darwin. So they go together. Pressure goes up and down together in the west end of the Pacific. And Samoa, about halfway across, that's on the other side of the line. So that's the other end of the seesaw. And this oscillation between the pressure at the east and west end of the Pacific came to be, well, he sort of christened it the Southern Oscillation, because most of these stations were, not all of them, but the important ones, Samoa and Darwin, were south of the equator. So this is what he called the Southern Oscillation. There's one kind of outlier on this list, the Southwest Canada temperature. You might think, what is that doing there? And a lot of Walker's colleagues thought that was pretty strange too. And in 1940, there was a correspondence in the Met Society, the Royal Met Society Journal, and he was called to question about it by one of his peers. And he said, "How can you? This doesn't make sense. This looks like just empirical relationships, and perhaps just sampling noise." And Walker was convinced that this correlation was statistically significant. And he said, "I admit, we don't understand it now, and we don't have the tools to understand it now. But someday we'll have upper air observations, and we will understand the reason for this. And meanwhile, all I can do is what I can do based on today's data." And he went back to his correlations. Well, now to jump ahead about 50 years, Jacob Bjerknes, who is arguably the man who recognized that this Southern Oscillation phenomenon of Walker's was related to something in the ocean, something very interesting in the ocean involving the sea surface temperatures along the equator and along the South American coast. His younger contemporary, Klaus Wörtke, who was working around the same time, was instrumental in identifying some of the key ocean elements of that. But Bjerknes also, although he was a meteorologist, and his early work, of course, was famous for identifying the structure of middle latitude cyclones, the so-called polar front anticyclones with their cold fronts and their warm fronts, as a young man in his 20s working in Norway, he had made those discoveries which really dominated synoptic meteorology for, well, into the 50s and 60s before those paradigms began to be questioned. So at the end of his career, Bjerknes got very interested in large-scale atmosphere-ocean interaction. And I had the pleasure of meeting him a few times at scientific meetings, and but I didn't recognize the significance of his work at the time, and I was sort of conservative, interested in my own work that I was doing, but as I go back to it now, his paper published in 1966, just 51 years ago, these ideas of how the wind along the surface, along the equator, changes the sea level, as you see at the top, and the depth of the thermocline, and implicitly the temperature of the upper layer, and the cross-section across the equator, how the thermocline bulges up when the wind is east, and it gets depressed when the wind is from the west. This were key figures from his paper. Actually, a lot of analysis in the paper, far more than I can take the time to reproduce. Another person I want to just mention briefly at the time, Joseph Fletcher, a man who tried but never managed to get a paper published, but he was a very visionary administrator in NOAA, and he mobilized a large group of people in the community to get interested in this El Nino phenomenon, the variations in the tropical ocean. And he had an advisory committee that was a place where I met and really got to know well some of the key people who were players in this. And Eugene Rasmussen, who was one of those people, and also, incidentally, one of my classmates at MIT in graduate school. And Gene, with his support scientist, Tom Carpenter, wrote a paper which, with this title, and you see the mention of southern oscillation and El Nino. And he, in this paper, recognizes the real unity of these two phenomena, that they're different faces of the same thing. And he credited Bjerknes with being really the first to recognize this. And the sketches here, this is a figure from this paper showing that the analysis in the paper was based on data along these lines that cross the equator. And these lines correspond to ship tracks. And ship tracks are important because they're places where there's dense data. Here, a modern day portrayal of the ship tracks. And you see these are just a few of these. And so in the paper, based on these analyses, or based on this formalism here, he was able to provide a very nice picture of the structure of El Nino along the equator. So in that picture, we have a real interaction between the atmosphere and ocean. Think of it almost like a dance with partners here, with the surface winds on the equator producing a circulation that produces big rainfall anomalies on the equator. And that was already known that some of the tropical islands in the central Pacific have tremendous variations in rainfall between the cold and the warm years, the El Nino years and the years in which the temperatures are cool. And those sea surface temperature anomalies and the rain, that influences the surface winds. The winds, in turn, drive the currents, as Bjerknes explained. And so it's a cycle, right, in which we have a variability happening that would not happen in a system with just the atmosphere by itself or just the ocean by itself. And so there was a lot of excitement in the community, and the intention to have a new program. And there was a real struggle to figure out the name for the program. And we had attempts like this, Southern Oscillation, El Nino. Somehow that just didn't work, didn't seem quite right. It didn't make a catchy acronym. And then suddenly, and I don't know if anybody knows exactly where this first came from, maybe Bill Patzert, but these names got juxtaposed, and El Nino got put first, and we ended up with ENSO. And I didn't discover till years later that ENSO is the name for this form of figure in calligraphy, which is actually a symbol. I'll let you read it here: absolute enlightenment, strength, elegance, the universe, and the void. What more could we want for a name for a phenomenon? And so ENSO became then the name for this interactive phenomenon, which is collectively El Nino, the ocean part, which was actually named after the ocean current along the coast of Peru, El Nino meaning the Christ child, and there's some history there I won't go into, but El Nino being the ocean part, and then the Southern Oscillation, the atmospheric part. So in the next segment of the talk, and it's going to be actually the major segment of it, I'm going to show you the structure of El Nino, but not as it was, as it appeared in the papers like Rasmussen's back in the 80s, but as it appears now. And I thought I'd start by mentioning all the remarkable data sets that have appeared on the scene since the time of the Rasmussen and Carpenter papers, since 1982. So in a way, this is this last 35 years of the century. And we had, and this first group is all based on satellite-borne instrumentation. We now have rainfall. Back in 1982, all we had was station data. But we had outgoing long-wave radiation, which is a pretty decent proxy for rainfall. That had started by the mid-70s, and then more recently in the 80s and 90s, we started to have a lot of microwave imagery, which is much more quantitative. And so telling us where it's raining, even over these vast stretches of ocean where there are no stations. Air temperature, and sea surface temperature, both remotely sensed, and giving us a much clearer idea of the patterns, much sharper analyses than back in the early times. And sea level now from the satellite altimetry, and I'm going to be showing you some sea level data connected with El Nino, or with ENSO, and chlorophyll, which provides a dramatic example of how ENSO affects the ocean. And then I should also mention another thing we have now that we didn't have then is back then all we had were a collection of univariate data sets. We had temperature, we had pressure, we had rain, but each one was a data set of its own. Now we have multivariate analysis where the whole is greater than the sum of the parts. By virtue of putting these data together into a dynamically consistent data set through this process of what we call data assimilation, the accuracy and quality control of these data is greatly improved. So not only do we have new data, but it's much, much higher quality in terms of accuracy. And we have that, we've had that for the atmosphere now going back to the 1990s, and we're starting to have some analyses for the ocean too. They've lagged because there isn't as much data, but they're getting, the ocean analyses are getting to be pretty good. I want to be sure I keep on time here. So I'm going to now show you a number of these variables, and I'm going to start with sea surface temperature. And I won't, at the beginning, I'm not going to show you where this pattern came from. I'm just going to say that this is the El Nino, or the ENSO temperature signature here. And during El Nino, it's warm in this belt, warmer than normal. And the warm colors indicate abnormally warm. The blue colors indicate abnormally cool, which there isn't anything very strong here. So if we average the temperature over this box, the sea surface temperature, every month, we can make a time series, and if we take out the ups and downs connected with the annual cycle, we can make a time series of the sea surface temperature anomalies. And this red curve here is that time series, and it's called Nino 3.4. The meteorologists in the audience will recognize that. It doesn't, I'm just going to call it the ENSO index. And when it's up, it means that this box is warm. When the index is down, it means that it's cold. And you can see that there have been ups and downs all through the last 110 years. Remarkable that the data are good enough so we actually can carry that time series all the way back to here. And we can think of this as if this were the seasons of ENSO, the variation between, think of this as maybe like summer and winter, but not summer and winter of the calendar, but summer and winter of this irregular ENSO cycle. And what I'm going to show you in the next couple of slides, what is anomalous or abnormal during summer, during the warm times. And those are the times we call El Nino, during El Nino events. So just as background, this is, I'm going to start with just a quick chlorophyll demonstration. This is the mean distribution of chlorophyll, and showing you that there's something special here about the equatorial Pacific. The green indicates a lot of turbidity of the water, and that's plankton, largely. So this is a very active area. This is a zone where there's a lot of fishing here and along the coast. These are the biological deserts, the dark blue. This is where the water is really clear. So this is satellite sensed through this so CWIFS imagery, as it's called. And so El Nino, or the ENSO, modulates the greenness of this belt along the equator. And here we see conditions as they were during, let's see, the date is on here. Yes, January 1998. That was in the middle of a very strong El Nino event. It was very warm on the equator. And notice it's blue all along the equator. There's no upwelling. No fishing, seabirds dying off for lack of food from those plankton, the whole food chain just dying at this time. And then here we are 6 months later, the middle of the next year, and it's all green again. In fact, it's greener than usual even. So there's been a big change from El Nino here to, as George Philander coined the term, La Nina here, the opposite, the cold phase. So now a couple of the other variables. Here is, and these, I should say, all of these maps are created from that time series that I just showed you, and by linear regression. And in effect, it's just a way of estimating what things are during, as if I could call it summer, during the times when that index is high. And these are the things that are abnormal. This is the sea surface temperature, and you see this belt along the equator, and it's just equatorial, and it affects the South American coast, but little else. There's not that much going on anywhere else. And at the same time, this is the pattern in sea level pressure. This is the pattern that Walker was trying to get at with his stations. And we see that at the time when it's warm here, when it's warm here, that the pressure, the sea level pressure is, the blue indicates low sea level pressure over the warm water, like a heat low. And also low offshore here. And we see the seesaw, the low on this end, high on this end. And Walker's stations, one group was in this area. It had Darwin, Manila. He was hitting the middle of this area. The other station was out here. That was the Polynesian station. So his index is a measure of this pattern. And here the two patterns are superimposed, and you see how this low fits over the warm, just fits like a glove. This is so it's like a heat low that we see during El Nino. Here are the here's the pressure again, the same thing we just looked at, and these are the winds during El Nino. And here they are together, and you see the winds blowing down the pressure gradient into this low along the equator. Not nearly as spectacular in these features off the equator, but this one seems to be attracting that wind, and the wind is blowing out of the high down the pressure gradient into the low. And we know from dynamics that there's something special along the equator. Within a few degrees of the equator, the wind can flow unimpeded by the Coriolis force isn't strong enough to deflect it. So we get, it's almost like we're draining a huge reservoir by having a jet along the equator. And so this is to say that relative to normal, the winds are in this sense along the equator. This winds again here, and this time this is sea level, and this is sensed by the satellite altimeters. So during El Nino, the sea level is above normal here. There's sometimes flooding in the estuaries and Ecuador, and it's below normal in the west, and sometimes there's damage to coral reefs when they get exposed because the sea level drops below them. And you can see here the wind superimposed on this pattern. You see how the wind is forcing this, pushing the water into this area with a high sea level and pulling it out of the area where the sea level is depressed. So the winds driving the currents, but sea level, sea surface temperature again, winds again, in terms of, we put these fields together, looks a lot like the last one, but the interpretation is that the wind is blowing into the regions of high sea surface temperature. It's converging into the places that are warm. So you can see that this belt of warm water here is really affecting the wind by deflecting it from its normal climatological pattern. And I think the last of this set is the rainfall. The winds again. This is the anomalous rainfall during El Nino. Heavy rain along the equator. Stations that are desert some years are flooded, like 10 inches of rain per month, month after month in this belt. And then drier than normal around the outer edge here. And you can see that we put these fields together. You see the wind converging into where the rainfall is heavy and diverging out of the regions that have deficient rainfall. So this low-level convergence of the wind field connected with the rain. I think I'll skip this one in the interest of time. This is the rainfall pattern again. This is the climatological rainfall pattern. This is just like out of an atlas. This is where it rains. The intertropical convergence zone, this is called the South Pacific convergence zone, the equatorial dry zone. This pattern is always there to some degree. But during El Nino, this part of it gets filled in. And you can see the two together here, and you can see that it's in effect these convergence zones encroach into the western edge of the dry zone during El Nino. So just to review, here are our four patterns together. And I'm going to show you, I'm going to compare three time series. We'll come back to this in a minute. And I want to just show one slide showing where these time series came from. The bottom one is sea surface temperature. It's the very one that we've been using to construct these maps that we've been looking at. Another one of the time series is the difference in sea level between San Francisco and Fremantle down near Perth. They're not in the seesaw here, but you notice how in sea level these patterns like have tentacles. This one comes out along the coast of Australia. This one goes up along the California coast. So we're going to look at a time series that is simply the sea level here minus the sea level here. And the third one, we're going to look at the difference in sea level pressure between this box and the rest of the tropics. We're sort of redefining the seesaw as this box that has most of the blue and the rest of the tropics which has most of the contrasting color. And so here we are again. So, so the bottom one is the sea surface temperature pattern. That was the middle one on the previous slide. This is the San Francisco minus Brisbane sea level. And this one is the difference between those boxes for sea level pressure. And in some ways, this is the punchline for how well this thing holds together. Because look, these three time series, we can match them up all the way back to even before the 1950s. And they match up just about perfectly. And so the red blotches here are El Nino events, and the blue are the La Nina events. So it just proves what Walker was trying to prove with his correlations, that these variables vary in a coherent way. It is just one pattern that explains this variability in all these different fields we've been looking at. So, let's see. So I'm going to just show, I'm going to skip a few things here. Just want to show the upper level pattern here, and this is up in the upper troposphere, around 15 kilometers or so. The geopotential height pattern, this is, think of it as the pressure pattern, and the wind pattern. These beautiful smooth gyres. Looks like something out of Matsuno's theoretical paper rather than something out of nature, where nature is usually messy. But up in the upper troposphere, it's very, very clean looking pattern. And these are other waves in Matsuno's family of waves, the equatorial Rossby waves, that are responsible for these and provide the theoretical interpretation of the ENSO pattern in the upper atmosphere. And finally, I want to show you that the Earth actually, the Earth's rotation slows down during El Nino. During El Nino, the days last longer. You can't get much more done because it's only a millisecond or so. But it is, the laws of physics require that angular momentum be conserved for the Earth system. And so we see three curves here, the red and the blue ones. One of those is the atmospheric angular momentum. It's calculated from the winds. It tells how fast the winds are circulating around the Earth. The other one, I forget which is red, which is blue, but they're almost the same, so it doesn't matter. The other one is the length of day as measured at the observatory in Boulder. No meteorologists. There's meteorologists in the building, but they don't go to those offices. So there hasn't been any collusion here. And look at how well they fit. And, of course, any physicist will tell you that this is just the laws of physics being acted out. If the atmosphere speeds up, the solid Earth has to slow down, or vice versa, because together they have to conserve angular momentum. So that's not surprising. But what is surprising is that, by and large, there's a pretty good correlation with the green line here, and that's the green line is the same ENSO index that I've been showing you. So during ENSO, the atmosphere speeds up, and the solid Earth slows down. And I think there actually is an explanation of that that has to do with the rainfall during El Nino and La Nina. So here is a profile from pole to pole showing the average rainfall, average around latitude circles. And we think of here as being two different climates, winter and summer for El Nino, for ENSO, the El Nino years and the La Nina years. And you see how during the El Nino years, there's a lot more of the rain falls close to the equator. And during the La Nina years, there's actually a break here, and we get a maximum at 7 degrees north for the intertropical convergence zone and a separate maximum here. Or if we take the difference between these curves, you see during El Nino, more rain in the deep tropics, less rain in the outer tropics. If we integrate over this whole curve, it's just about the same, but it's just a redistribution. And so it's like during El Nino, we concentrate the rain on the equator. During La Nina, it's spread out more. And so if we think of the ice skater analogy with angular momentum, if we take air that's got the biggest moment arm and lift it up into the upper troposphere and then have it go poleward, conserving angular momentum, it's going to be spinning faster than the air that hasn't come up, doesn't have quite as big a moment arm. And so I think that's the basic thing that's going on here. I think I'm going to skip through a couple of these and just come back to just show you two quick things, and then I'm going to end. Wanted to everything I've shown you so far is about the atmosphere, and I want to show you what ENSO looks like in the ocean. And this is based on recent analysis of the subsurface data, one of these so-called data assimilated products produced by this group in Japan. And Komoto was a visitor here for Masa Komoto, worked with Michael Gill here at UCLA for a number of years. So he's back in Japan, and he was contributed to the production of this data set. So the first pattern shows the integrated heat content in the upper layers, which matches the sea level signature very well. And then these curves, these panels show you where this heat is distributed. This one is along the equator, just an east-west cross-section. And you see this warm blob here is a very shallow warmth of the boundary layer here. And then the blue, where the heat content is less, this is deeper. And this feature here is very narrowly focused on the equator. This one actually has two lobes off the equator. And again, we come back to Matsuno again. The oceanographers recognize this as Matsuno's waves again. This one, the Kelvin wave on the east, and the Rossby wave on the west. So the beautiful symmetry of ENSO in the ocean as well as the atmosphere. And then I wanted, since this is Los Angeles, and this is a place where people are very skeptical about climate forecasts relating to ENSO and rainfall, I wanted to end with a little something on that. So just in the same way as we looked at patterns in the other fields, we can look at the upper level patterns over the whole northern hemisphere that help to interpret our anomalous weather, our variations in weather from year to year. This is a figure that we produced back in 1981 based on the data that was available then. This figure is based on data from 1979 onward. There's virtually no overlap in the data that went into this and went into this. So in a way, this is like performing an experiment again to verify something that we thought we knew. And you can see the very nice correspondence between these patterns. This blob here goes with this goes with this dipole goes with this. So it's been very nice to see nature kind of repeating itself. And when we have strong El Niños, this pattern appears very strongly. This was 1982-83. This was the biggest one that had been observed up to that time. And notice the classic dipole pattern and this downstream feature. This one, 1997-98, remarkably similar. And what was going to be the mother of all El Niños, the one last year, well, it's not quite, it didn't turn out to be quite as strong as the others, but it's still respectable in the tropics, but doesn't look quite right in terms of the patterns in the northern hemisphere. So quite a bit different from these, not as distinct. And so what does that mean in terms of California rainfall? Well, that's one of my colleagues, Shanyao Chen, produced this next very short set of figures. This is the historical record of rainfall in Southern California, station data, only a couple of stations going back this far, and then more stations coming in. You see the big ups and downs, and of course, you're familiar with that. And so we want to know, what does El Nino or ENSO contribute to this? Well, if we make a plot based on all the data up to 2015, doesn't include last winter, doesn't include this winter, this is what we get. This is the ENSO index, the same ENSO index I was using for all the other figures. This is the rainfall from that time series. So you see there is a correlation when the ENSO index is positive, that's like ENSO summer, and it's warm in the equatorial Pacific. On average, it does rain more than when it's cold, but if you were going to Las Vegas and you had these kind of odds, I don't think you'd be putting very much money on the line just because maybe you knew what this was and the prize was going to depend upon what this is. So as it turned out, this relationship didn't work out very well for the last 2 winters. I just put in numbers here for the years, a guess of where these years might lie. We don't actually have the data yet. This winter might not even be finished yet. But this 2017 winter, near record rainfall and slightly negative index. It was La Nina, but only just by a hair's breadth. The previous winter, it was a strong El Nino, high index here, one of the big ones, and below normal rainfall. These numbers don't look like they're unprecedented by any means. It's just, they certainly don't help the relationship, but it doesn't mean that a paradigm is broken. It just means that we're using a relationship that only explains a small part of the variance, and the circulation in middle latitudes has a life of its own. El Nino is not the only thing that the California rainfall cares about. There's a lot of other things as well, and during these years, the other things were paramount in determining what happened. So I think I will stop here. I just wanted, in way of rounding things out, I wanted to thank a couple of people who helped me put this together and made a lot of the made the figures that I showed. So I want to end by thanking you very much for your attention, and I hope this will perhaps increase your enjoyment of El Nino, if nothing more. Thank you.
Surely when you do correlations in the rainfall here with the ENSO index at a fixed point, it doesn't tell me whether the rainfall just moved somewhere else and was still very intense, but somewhere else.
That's certainly true for daily rainfall. When you get to seasonal rainfall, there's more coherence, more spatial coherence to it. But still, I would agree with you, one station does not define Southern California. But after that time series that I did show, from 1950 onward,